Welcome back to What is Time Part 3 with P. Edward Swan. If we want to conquer the solar system, we need to conquer time. Time has always been important for navigation. In the first video, What is Time Part 1, we found that it is difficult to synchronize two clocks when those two clocks are experiencing different environmental interactions. Remember the trip around the solar system? If we take just one of the two clocks on a journey through the solar system, we want the two clocks to be synchronized at every step of the journey. But this is a difficult challenge because any environmental interactions such as gravitational fields or any accelerations will cause a variance in the two clocks that will need to be corrected. To master time, we need a framework to track all of the environmental interactions and then use relativistic equations to account for any differences. Can we use the clocks themselves to detect these environmental interactions? In the second video, What is Time Part 2, we explored the relationship between the internal information processed by a clock and its clock cycles. The more information that a clock system is processing, the more its clock cycles become elongated. Therefore, a clock that is processing more information will produce less clock cycles when compared to a clock of identical construction that has less information to process. We can use this fundamental relationship to detect various environmental interactions. Whenever we have two or more clocks of identical construction, we can use the difference in their recorded clock cycles to measure environmental factors and interactions. And this chart is just to remind us that moving clocks run slow. Light clock A was moving, and it takes 22 steps to produce one clock cycle, and light clock B was at rest, and it only takes 20 steps to produce one clock cycle. And the difference between these clocks is only the acceleration experienced by clock A, which creates a variance. And that variance we're going to use to help us detect environmental interactions. In this video, we will use two clocks of identical construction to show how multiple clocks can be used to detect the fundamental changes that are taking place in a clock system related to motion. We will demonstrate how clocks can be used to answer an old challenge posed by Albert Einstein and his colleagues. It took me almost 4 decades to imagine an experiment that will solve this puzzle. The challenge is as follows. If we are in a spaceship traveling through space in uniform motion in a straight line, there is no experiment that we can do to determine the non-relativistic speed of the ship. In other words, is the ship moving? Or is the stars just moving by? Or both, some combination of both? In other words, can we imagine a test to determine how fast the spaceship is moving against some universal frame of reference? If we can find the answer to this question, it also means we can determine if a clock has zero velocity, which we will also examine very briefly later in the video. To begin the thought experiment, we must imagine that there is a very massive spaceship that is traveling through space with velocity v in some unknown direction. The velocity is unknown, but it must be at least zero and less than the speed of light. On board this ship, we must also imagine that we have two ultra-precision clocks of identical construction, clock A and clock B. These clocks will show a variance at the tiniest influence. And finally, we must imagine that on this ship we have a clock accelerator. The clock accelerator is a mechanical machine that is able to accelerate clock A to 10% of the speed of light relative to the reference clock, clock B. The clock accelerator moves just clock A back and forth over a very short distance of 10 meters. The clock accelerator is fixed to the very massive ship, and any equal and opposite forces will only accelerate the massive ship and the reference clock by a tiny amount that is ignored for this thought experiment. The experiment that will answer the challenge has two parts. The first part is to find the direction of motion of the spaceship, and the second part is to find the velocity of the spaceship. To set up the experiment, we will imagine two ultra-precision clocks of identical construction. Next, we must pick a random velocity v for the spaceship that we will not know. We will use this unknown velocity to generate the results of our clock tests. The end goal is to indirectly calculate the unknown velocity by counting clock cycles and only by counting clock cycles. To keep this thought experiment as simple as possible, we will limit the direction of the velocity to the xy plane. The unknown velocity will have a direction given by the angle 1/8 pi from the x-axis and a speed that is 8% of the speed of light as seen in the figure. Now we can begin our tests. On the spaceship, we will use the clock accelerator to increase the velocity of clock A along the x-axis, movement north and south. We accelerate clock A to 10% of the speed of light in the y direction, north, for 10 meters, and then it is decelerated back to 0 speed. Then we accelerate clock A in the negative y direction, south, for 10 meters and back down to 0 again as it returns to its original position. First we're going to check the north and south direction, and then we're going to turn the accelerator to the east and west direction and check the east and west direction, and that will be coming up soon. Also, these accelerators are of course fictional. They don't exist. We don't have access to this kind of technology where we can accelerate a clock to 10% of the speed of light in this very short distance. It's great for thought experiments and it's great for the calculations. It helps to do the calculations easy. But eventually we will be talking about something more practical, some machines that we may actually be able to build. And we'll be talking about that at the end of this video series. In this figure, we see the velocity curve for clock A relative to the spaceship. The velocity curve is mapped by distance. It takes 5 meters for the accelerator to reach full speed, 10% of the speed of light. It remains at full speed for 10 meters, and then it takes 5 more meters to return back to speed 0, all in the north direction. We start counting the clock cycles of clock A when the accelerator reaches full speed, the green dashed line, and we stop counting the clock cycles of clock A when the accelerator begins to slow down, the red dashed line, as shown in the figure. In this way, we can use the mechanical motion of the accelerator to start and stop the recordings that count the clock cycles for clock A. And here we can see the velocity curve for this clock accelerator. It goes from 0 to around 30 million meters per second. It stays at that rate until the 15-meter mark, and then it returns back down to 0 meters per second by the 20-meter mark. And here's another visual. The clock is moving in the north direction, and it gets accelerated over 5 meters until it reaches 10% of the speed of light. It stays at 10% of the speed of light for 10 meters, and then it begins to slow down over the next 5 meters until it reaches 0 meters per second at the end of this one run. We repeat the same process for clock A, but this time the accelerator moves clock A in the south direction by the same acceleration curve, and clock A is returned to its original position. Again, we only count the clock cycles when clock A is moving at full speed in the south direction this time for 10 meters. Please notice that our inputs, the known quantities for this test, are the amount of work, known quantity number 1, that is needed to accelerate a clock, clock A, of some mass, known quantity number 2, to 10% of the speed of light in some direction, north or south, known quantity number 3, over a distance, known quantity number 4, which is 5 meters. And the idea behind the known quantities, these are things that we can measure on the ship. We can measure the mass of the clock. That's a known quantity. We could have measured it back on Earth. We could measure it wherever we measured it, but it's a mass and that mass doesn't change. We can also measure the amount of energy. We know the amount of energy that it takes to accelerate a mass that we know over a certain distance to some velocity, 10% of the speed of light. So we know those are known quantities that we can measure on the ship. We don't need to determine them relativistically. And so that's the whole idea behind this, is that these are all things that we can do on the ship, and we can perform these experiments without knowing any additional information except what we can measure. Now we simply use vector addition to find the combined velocity vectors that clock A will be experiencing when the clock accelerator is activated. To add two vectors, we just add the components. We have to do this for both directions, and we get the two vectors shown in the graph. Okay, so now we have two velocity vectors for clock A while it was in the clock accelerator. We have the north velocity vector and the south additional velocity vector. And we add those to the base velocity vector of the spaceship, which is this blue velocity vector. And we come up with two new vectors, the totals for the blue and the green, and the total for the blue and the red, right there. And we don't know what they are yet, but we will see how we can use those in the next slide. We can notice that the vectors are not equal. The vector in the north direction is longer than the vector in the south direction. The longer vector represents a greater speed. Because moving clocks run slow, and clock A has a greater speed in the north direction, then it will record less clock cycles over the same distance compared to clock A when moving in the south direction. We do not know the velocity of the spaceship, therefore we have to calculate it indirectly by observing the clock cycles of clock A and clock B. However, we are only using clock A for this part of the process. And here we have the two velocity vectors that we do not know. These are unknown total velocity vectors from when clock A was in the clock accelerator, once going north and once going south. But what we do know is how many clock cycles were produced by the clock. Clock A, when moving in the north direction, produced less clock cycles than the same clock A when moving in the south direction. It produced more clock cycles. And since moving clocks run slow, clock A, when moving in the north direction, was moving at a greater velocity. That's the only thing we know. We know that this vector is longer than this vector, greater velocity, less velocity, because of the clock cycles that were produced by the clock while we perform the tests. Because clock A is recording more clock cycles when moving in the south direction, then the motion of the spaceship cannot be in the south direction. We know this based on vector addition. The north direction component of the spaceship's base velocity vector adds in the north direction but subtracts in the south direction. And so we can eliminate the negative y portion of the map as a possibility for the spaceship's velocity vector. But we still need more tests to pinpoint the velocity vector of the ship. There is at least one other vector that would give the same results. And remember that this set of experiments, we're only trying to determine the direction of the spaceship for the first part of our testing. And so we're trying to determine what this base velocity of the spaceship is, which direction the spaceship is moving. We don't know the magnitude and we don't know the direction, and right now we're just trying to find the direction. And what we do know, when we accelerate the clock in the north direction and the south direction, then we're testing the north-south component of this spaceship space velocity vector. And here you can see that it's just this little distance right here between the yellow dotted lines. That is the north component of this blue vector. And it adds in the north direction, but it subtracts in the south direction, and that's why the total velocity vector is smaller in the south direction, but it's longer in the north direction. And so that's how we know we can eliminate the south direction as a direction for the base velocity vector of the spaceship. Now we can rotate the accelerator to the east-west direction, and we can repeat the same test. We accelerate clock A in the east direction at 10% of the speed of light for 10 meters, and then back again in the west direction at 10% of the speed of light for 10 meters. The accelerator has the exact same acceleration curves as before. Now we add the east-west vectors to the spaceship's constant base velocity vector, and we have the following total velocity vectors as shown in the figure. we can see that the total east vector is longer than the total west vector. Therefore, clock A is moving at a greater speed after the acceleration in the east direction compared to a lesser speed after the same magnitude acceleration in the west direction. However, we do not know the total velocity vectors for clock A while it was in the accelerator. We only know the velocity vectors for clock A from the actual acceleration, but we don't know the total vectors. But what we do know is how many clock cycles were recorded by those clocks, by clock A in each of the two tests. Clock A recorded less clock cycles when moving in the east direction. Clock A recorded more clock cycles when moving in the west direction. Since moving clocks run slow, less clock cycles means you were moving at a greater rate. So we know that the total velocity vector in the east direction is greater than the total velocity vector in the west direction. And that's again because of vector addition. We have the total component for the spaceship's base velocity vector in the east direction is the amount between these two yellow dotted lines, and that adds in the east direction, but it subtracts in the west direction. And so that's how we know that the spaceship is moving in the east direction. As before, because moving clocks run slow, clock A will record less clock cycles when moving in the east direction compared to clock A when moving in the west direction. Therefore, the velocity of the spaceship must be in the east direction, and we can eliminate the negative x portion of the map as a possibility for the spaceship's velocity vector. By trial and error, or after collecting enough data points by direct mathematical calculation, we can find the angle where the accelerator is exactly perpendicular to the velocity vector of the spaceship. The accelerator angle is exactly perpendicular to the velocity vector of the spaceship when the additional velocity vectors produce two new vectors that are equal length. When the accelerator has an angle that is 5/8 pi from the x-axis, then the accelerator is perpendicular to the velocity vector of the spaceship. When the accelerator is at an angle of 5/8 pi from the x-axis, clock A produces an equal number of clock cycles in each direction. Therefore, the total velocities must be equal. If we add the vectors, we find that the two new total velocity vectors are exactly equal length. The only two cases where the total velocity vectors are equal is when the base velocity vector of the spaceship is perpendicular to the additional velocity vectors, or the case shown on the next slide. Because 5/8 pi is perpendicular to the base velocity vector, then we can calculate the direction of the base velocity vector of the spaceship. Okay, so finally we can calculate the direction of the base velocity vector of the spaceship, which is the first part of the tests that we're trying to accomplish. We know these new velocity vectors are perpendicular to the velocity vector of the spaceship because when we're performing our tests, the clock A is producing an equal number of cycles in either direction. This northwest and southeast directions. And so, since it's perpendicular, we know that this is 5/8 pi, that's this angle, and we know that it's 90 degrees difference, which is 4/8 pi is 90 degrees. So we can take 5/8 pi minus 4/8 pi, and that leaves us with 1/8 pi, and that's the direction of the base velocity vector of the spaceship, and we've accomplished the first part of our testing. Here we will stop for a moment and highlight what we found in the last slide. When the velocity vectors are equal, there is no base velocity for the spaceship in that specific direction. If we perform the accelerator test 3 times along the x-axis, the y-axis, and the z-axis, and the new total velocity vectors are equal in each case, that is, clock A produces the same number of clock cycles for every test, then the base velocity of the spaceship is 0 in every direction. This is the test that can prove if a spaceship is at rest relative to a universal frame of reference. If the spaceship has a base velocity vector that is greater than 0 in at least one direction, then at least one pair of the additional velocity vectors would be offset by the base velocity vector of the spaceship. In the figure, the base velocity of the spaceship is northeast and limited to the xy plane. Clock A will show a variance when accelerated in both the x and y directions. Okay, so if we perform 3 tests, which each have 2 sides, so a z positive and a z negative, up, down, north, south, east, west, and that would be putting the clock and the accelerator in 3 different directions, all of these, the major directions, then the only way that the clocks would produce the same number of clock cycles is if the clocks were all moving at the same velocity. And that's only possible if there was no velocity of the spaceship, right? So if the spaceship had a base velocity vector, and in this case, this is the gold vector, right? The spaceship's base velocity vector is this little gold vector, then it shifts those tests in some way. Now this vector adds to these 2 vectors here, the east direction and the north direction, and it subtracts from the south direction and the west direction, and it's neutral to it's perpendicular to the z positive up direction and the z negative down direction. So these 2, the clocks would produce the same number of clock cycles, but for the other 2 tests, the clock cycles would show a variance. And if any of the clock cycles show a variance, then there is a base velocity vector for the spaceship that is greater than 0. So that's how you know if something is at rest relative to the universal frame of reference. This test will tell you that. Please join me for What is Time Part 4, where we will continue to work on the difficulties we face when we try to synchronize 2 or more clocks that are subjected to different environmental interactions. In Part 4, we will use the relationship between clock cycles and the information particles of energy/motion, that is, moving clocks run slow, to calculate the environmental variables related to motion that are present in all physical objects. In this part, we found the direction of the base velocity vector of the spaceship. In Part 4, we will calculate the speed of the spaceship. To do this, we will use the ideal clock, which is a universal reference for time. The ideal clock is a clock that has 0 motion, 0 gravity, standard heat, and so forth. Real-world clocks are imperfect. Therefore, the ideal clock is only a mathematical construct. But everything in the real world is imperfect, so we must make do. Thank you for watching, and please like this video, share this video, and subscribe to this channel. In my book, Darwin's Machines, you will find a variety of fascinating topics such as time, space, the Big Bang, and free will. If you like science, you will love Darwin's Machines, an information systems approach to understanding the natural world. Please see the links below where you can purchase my book. Also, I am currently working on human longevity technologies so we can all live longer and better lives. Over the last 20 years, I have developed a groundbreaking design for biomedical sensors that will revolutionize the $200 billion per year medical devices market. If you would like to help me bring this product to market, please contact me by email, or you can also support my work by purchasing my books. I am looking for people with all kinds of backgrounds to help me with every aspect of the project, including the technical, organizational, funding, networking, and everything in between. Thank you for your support, and be well.